Okay, as you guys learned in lab or messed around with in lab the other day, you guys know that temperature is actually a measure of the average kinetic energy of the particles. I'm not sure if we made that abundantly clear or not, but when you cooled down the particles, the temperature dropped and the pressure went down because the particles stopped bouncing off the walls, and we extrapolated that out to absolute zero. Okay, so temperature, and this is kind of important, temperature measures average kinetic energy. Okay, now the most important part of that is the average part. Okay, it measures the average kinetic energy of the particles in a substance. Okay, now what do I mean when I say particles? I mean the atoms, the molecules, the ions, the things that make it up, the tiny little particles that make it up. Those are the particles in an object. That's what I'm talking about. Okay. When I say the average kinetic energy, I mean this is independent of mass. A hot object and a cold object have different temperatures. They could have the same thermal energy. That's a little ahead of where I want to be. But two different sized objects can have exactly the same temperature, right? An iceberg floating in the ocean and an ice cube floating in your glass of water can have the same temperature. Both the particles are all the particles in ice are they're all moving fairly slow. So if they're all at the same temperature, they have the same average kinetic energy. It's independent of the mass. Okay? Thermal energy is different than temperature. Temperature does not measure thermal energy. It's a part of thermal energy, but it's not all of thermal energy. Okay? And since temperature is a measure of the average kinetic energy, we really tend to use the Kelvin scale. Okay, so there's three temperature scales that are pretty prevalent: Kelvin, Fahrenheit, and Celsius. The Kelvin scale is nice because it's absolute. Okay, and I mean that in that it has an absolute zero. Okay, Kelvin scale is the absolute scale. 0 Kelvin is absolute zero. Okay, there is no temperature colder than that. Remember, kinetic energy is 1/2 mv squared. Okay, so it's nice to have a temperature scale that starts at absolute zero because then we eliminate this thought that maybe there could be negative kinetic energy. There's not. A negative temperature on the Celsius scale means it's below the arbitrary zero, and the arbitrary zero on the Celsius scale is the freezing point of water. The arbitrary zero on the Fahrenheit scale is the freezing point of water with antifreeze, right? But the zero on the Kelvin scale is absolute zero. Okay, absolute zero means the particles have stopped moving. Okay, so kinetic energy of the particles is zero. They cannot lose any more energy. And remember, 0 Kelvin is equal to negative 273.15. That's negative 273.15 degrees Celsius. And the cool thing about the Kelvin scale and the Celsius scale is they were set up to have a change equal to each other. So if I add 1 Kelvin over here, it's the same as adding 1 degree Celsius over here. Okay, so we can convert easily between Kelvin and Celsius. Degrees Celsius, not degree, yeah, degrees Celsius, minus 273.15 equals the temperature in kelvins, right? So it's pretty easy to convert back and forth between these two scales. And the cool thing about it is there is no such thing as negative Kelvin. Okay, so we use Kelvin when we're using SI units, although since a degree Celsius and a degree Kelvin, or just a Kelvin, have the same magnitude, if we're talking about a change in temperature, a change of 18 degrees Celsius and a change of 18 Kelvin is the same magnitude. Okay. Now, what temperature is not thermal energy. Okay. Thermal energy is more than just kinetic energy. Thermal energy is the total energy of the molecules and ions and atoms that make up matter. Total energy of, I'm going to say, the molecules in an object. The molecules in an object. Okay, so is temperature a part of that? Well, absolutely. Okay, so this includes temperature because the more temperature something has, the faster the particles move, so the more energy they have. So it includes temperature, but it also includes mass, right? And why would mass matter? Well, if something has more particles, it's going to have more energy. So it includes temp and mass. And by mass, what I'm really getting at is the number of particles, right? The more atoms, molecules that it's made out of, the more energy it has. And there's one other thing that this includes, okay? It also includes phase or state or how the particles are arranged. So includes phase. I'm going to say arrangement and forces between particles. Just like gravitational potential energy exists because there's a force of attraction between two objects with mass, there's forces of attraction between molecules, and those are going to mess with its thermal energy. So it includes phase, arrangement, and forces on the particles or of the particles. Okay, so we're going to see that the phase, the solid liquid gas thing, kind of makes a difference in thermal energy. Okay, so the cool thing to remember is objects of unequal mass can have the same temperature. So consider like a giant pitcher of lemonade, or I guess maybe it's supposed to be snowy and cold. So let's say we have a giant pitcher of hot coffee, right? It's completely full. It's really, really hot. We pour a little cup full of hot coffee. It's completely full. It's really, really hot. The temp for both of those is the same, but this one has more thermal energy, and it's got more thermal energy because this one has less mass. There's less particles in it. Okay, you can kind of think of thermal energy as what would happen if you mixed them together, right? If I had a giant iceberg and I had an ice cube, they're both really, really cold. They have the same temperature. But if I pour a glass of hot water on an ice cube, the ice cube melts. If I pour a glass of hot water on an iceberg, my glass of hot water becomes very, very cold water, right? There's this whole mass difference that you have to take into account. So thermal energy is more than just temperature, and it includes the mass and stuff. So what does temperature actually do? How do we measure it? Okay, thermometers rely on energy transfer. Thermometers work because thermal energy can move. Okay, now this is kind of interesting because thermal energy flows. A thermometer can only ever measure its own temperature. So if you've got a bucket full of ice water, okay, and I stick a thermometer in there, the liquid in the thermometer starts to drop, 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 drop. Okay, and that's because this thermometer is actually transferring heat or energy to the water, and it transfers until the temperatures match. Okay, so thermal energy flows from one object to another until the temperatures are even. Okay, now this is a little bit weird. This means that energy is not necessarily going to go from highest energy to lowest energy. It goes from high temperature to low temperature. Thermal energy flows from hot to cold. Okay, now that is something you guys are all very, very aware of. You don't put a glass of hot water on the, or hot coffee or whatever, on the counter and expect it to sit there and get hotter and hotter and hotter and hotter. You know it's going to cool down. It's going to lose its energy to the room. Okay, energy flows, thermal energy flows from hot to cold. It does it spontaneously all by itself. This thermometer stopped changing when these two things, the liquid it's in and itself, are the same temperature. And when that happens, okay, when the temperatures balance, we have what's called thermal equilibrium. Okay, so when temps balance, we have thermal equilibrium. Now, for the very, very longest time, there was a lot of debate going on in the scientific community of what heat actually is, or what thermal energy actually is, or what temperature is actually measuring. How are all these things related, right? And in fact, you guys are still aware of some of this debate that still is left over today. If you've ever looked at the caloric content or the calories in food, this is an old measure of energy, okay? Caloric was thought to be a fluid that was heat. Okay, things that were hot had caloric, and things that were cold didn't have caloric. and you could move caloric from one thing into another, and caloric would flow until temperatures matched. But caloric referred to this mysterious fluid substance that hot objects had and cold objects didn't. Okay, and it wasn't until James Prescott Joule came around in this, I'm not exactly sure when, that we started to actually understand that heat, thermal energy, they're not any different than mechanical energy, and we can get work or useful work out of them. Okay, so Joule, the guy who actually named the energy unit 4, did this cool experiment where in fact, I'll just show you a picture. Okay, he took a paddle wheel, that's this thing right here, put it in a bucket full of water, big old barrel of water, wound a rope around this thing, put a hanging mass over here, okay, let it fall, and measured the change in temperature of the water. He noticed the water got warmer as this mass fell, as the water started to move. Okay, and he was able to relate the energy of the mass as it fell, right? Because it's losing its potential energy here, and when it hits the ground, it still doesn't have any energy, and that energy had to go somewhere. And Joule is saying, well, that energy goes right here. It's not a mysterious fluid caloric that goes in there. It's actually thermal energy is energy. It's the same as mechanical energy. It's just instead of making an object move, it's making the particles inside the object move. Okay, so Joule, the reason we use the Joule for our unit of energy is because Joule realized that thermal energy and energy are the same thing. So thermal energy is transferred from hot to cold, and we call that transfer heat. Okay, and heat is basically work. Okay, remember, work is the change. When you do work on an object, you give it energy. So when you do work to lift an object, you give it gravitational potential energy. When you do work to accelerate an object, you increase its kinetic energy. When you do work to slow down an object and stop it, you decrease its energy, but that work goes into making thermal energy. Okay, so you heat up the surroundings. All right, now heat is the flow of thermal energy. Heat is the flow of thermal energy. Okay, and it flows spontaneously from hot to cold. It happens all by itself, and it's given the symbol Q. Okay, so Q is heat. Now, not all things gain thermal energy. Some things lose thermal energy. Okay, so heat can be positive or negative, just like work can be positive or negative. Okay, if Q is positive Q, then heat is gained, or heat is absorbed, or thermal energy increases, heat absorbed, and temperature goes up, generally speaking. Okay, if Q is negative, then heat is lost, temperature goes down. Okay? Now, measuring how much heat something's gained or lost is actually kind of a tricky thing to do, because it does depend on mass, it does depend on temperature, and it depends on one other quantity. I don't know if you guys have ever been to the beach, but if you've ever been to the beach, you know you've got sandy beach, water. I guess I could make my water blue. Okay, water here. Okay, sand gets really hot. Water doesn't. Stays the same pretty much all the time, right? When it gets cold out, it takes a really long time for water to freeze. On the summer, you jump in the lake at night, it's still basically the same temperature as it was in the daytime. The sand, on the other hand, gets hot and cold, hot and cold, hot and cold, hot and cold. Okay, so something's ability to change temperature or heat up or cool down, okay, heating up depends on lots of things. Depends on mass. Okay, it also depends on material, and it also depends on the temperature difference. Okay, so the amount of heat gained or lost depends on how much stuff is actually gaining or losing energy, how much the temperature changes, and also on what it is. Okay, water is hard to change temperature. Sand is pretty easy to change temperature. And so this is the idea of specific heat or heat capacity. Okay, these are two terms that mean the same thing. Something's ability to contain heat, or the amount of heat required to raise the temperature of 1 kilogram or gram of an object by 1 degree Celsius or Kelvin or Fahrenheit. Okay, so the reason we get specific heat is this is actually amount of energy required to raise the temp of the temp of one. It depends on what unit you're using. On the temp of, we'll say kilograms. The temp of 1 kilogram of matter by 1 Kelvin or 1 degree Celsius, since the magnitude is the same. Okay. Now, this was not the first unit used. Okay, back when Joule was doing this, he was doing degrees Fahrenheit, and he was using pounds, and he was doing all kinds of things. Okay, but the calorie that you see today is actually 1,000 calories. It's a kilocalorie with the capital C, and 1 lowercase calorie. Okay, so a calorie is 1,000 lowercase calories. This is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so when you see the energy content of food measured in capital C calories, like, I don't know, 120 calories, that's 120,000 calories, and there's enough energy in there to raise 120,000 grams of water by 1 degree Celsius if you were able to burn that entire sample of food. Okay, so that's what calories actually measure. They measure heat. They measure the heat or energy contained in something. Okay, so specific heat is the amount of energy required to raise the temp of 1 kilogram of batter by 1 Kelvin or 1 degree Celsius. Water has a very, very high specific heat. Okay, we don't use calories, we use joules and kilograms. So the specific heat for water is like 4.18 joules per gram degree Celsius. And we're going to use that one over and over and over and over again. Okay. Heat capacity is the same thing. It's another term for specific heat. It describes something's ability to store or hold thermal energy. The higher its specific heat, or the higher its heat capacity, the more energy it actually takes to cause its temperature to change. So we have this equation: Q equals M times C times delta T. Okay, where M is mass, C is specific heat, and delta T is change in temperature. Now, it doesn't matter if you use kelvins or degrees Celsius, because the magnitude of 1 Kelvin and the magnitude of 1 degree Celsius are the same. But if the temperature goes down, then this heat is lost, so your Q is negative. If the temperature goes up, the heat is gained and the Q is positive, right? So mass is measured in kilograms, M specific heat, joules per kilogram degree Celsius, or joules, kilogram, Kelvin, doesn't matter, and temperature degrees Celsius or Kelvin. So there's an example problem in the book on page 318, and it gives you the mass of iron. It tells you its change in temperature, and there's a table of specific heats on page 200 or 318 in your book. Okay, so I'll run through the problem. It says a 5.1 kilogram skillet is heated from 295 to 450 Kelvin. Okay, 295 to 450 Kelvin. Now, is that very hot? Well, 273 is room temperature Kelvin, or is 0 Celsius, right? So this is about room temperature up to 450. So yeah, that's pretty hot. 450 Kelvin is right around 180 Celsius, which is right around 350 or so Fahrenheit. Okay, so you wouldn't want to touch it. So it's getting warm. And iron, if I look in the table, has a specific heat of 450. C is 450 joules per kilogram Kelvin. All right, so I want to know how much heat it was absorbed by the skillet, how much heat was required to get this done. So I'm going to take QMC delta T, so I have mass, 5.1, times the specific heat, which is 450, times the change in temperature. It went from 295 to 450. That is 155 Kelvin. And if we actually do this math, this is about 3.6 times 10 to the fifth joules, right? Why is it joules? Well, because specific heat is joules per kilogram Kelvin. We multiplied it by mass in kilograms and temperature change in Kelvin, and we're left with joules, okay? So we can see that the energy required to heat something up and the work done heating it are basically the same thing. Work and heat are equivalent, and that is really cool, okay? So I will assign some problems from this, and we will do a lab probably Wednesday or Thursday based on heat, temperature, and energy.